Welcome back. In my last two talks, I introduced you to positivism and interpretivism. Today, we're going to continue with these two epistemologies and examine how they make claims to have found knowledge. In doing this, it provides a means for me to compare and assess the two epistemologies. I will argue that while they represent seemingly polar opposites in the assumptions that they make about the world and about knowledge, at the same time, the way in which they claim to have achieved knowledge is not so far apart. Let's begin with positivism. The term originates with Comte, but the modern understanding of positivism, I noted this, arose with the Vienna, the Vienna Circle, that developed on the eve of World War I and continued in its aftermath. They sought to find logical warrants for science to make truth claims. Initially, they focused on verification, but were convinced by Karl Popper's argument that this was inadequate because you might always come up with something that didn't verify it. So the example that he used were swans. That if you said all swans were white, you looked everywhere in ponds and lakes and you found only white swans, you still couldn't say that all swans were white because you'd never know when a black swan would come along. For this reason, it made sense to look for the black swans at the outset. In other words, to try to falsify hypotheses and theories. To do this, the theories had to be set up in a way that they lent themselves to falsification. Their terms had to be clear, their scope specified, and scientists had to avoid using the equivalent of bubble gum and rubber bands to patch them up every time they were shown to be wrong. They had to acknowledge that they had failed. So ultimately, Popper argued, and this is a point I'll come back to, science might rest on its procedures, but for those procedures to be followed in an honest way, science had to become an ethical practice, and scientists had to become ethical people, especially those at the top of the field who functioned as gatekeepers. Positivism and its subsequent formulation of neo-positivism had significant impact in the social sciences, where they became the sort of ideological underpinnings or foundations for the behavioral social science enterprise. They had less impact, this too I noted, in the sciences, because science marched to its own drum and really didn't feel the need, even resented the need, of intervention by philosophers. Scientists don't really conform to the edicts and procedures of the Vienna School and Karl Popper. Let me give you a couple of examples. Popper stresses falsification, and indeed, theories that can be falsified, scientists reject or attempt to reformulate in ways that will prevent that from happening again. But scientists are deeply impressed as well by verifications. Einstein's general theory of relativity. Among other things, it interpreted space-time in such a way to offer a radical explanation of gravity. From this could be inferred that light, in other words, photons, are bent when they pass in the vicinity of something very massive, like a sun. After the First World War, Eddington, who was head of the Royal Observatory in Britain, tested this during an eclipse. The sun was covered by the moon, so one could take photographs of stars in the vicinity, which you couldn't possibly do in daylight. Where those stars were on the photographic plate could be compared with where they were on that plate when the sun was nowhere in the vicinity. And lo and behold, just as Einstein predicted, the light had been bent, and his predictions were accurate out to about 5 places, which was a remarkable proof. There were several other proofs of relativity, each of which made scientists believe that this was likely to be truthful. So it achieved a high degree of provisional truth, not through failure to falsify it, but rather attempts to verify it. The other thing that is important for science are mechanisms. Why is it that something happens? It's not enough to say that A and B are closely associated. If we posit A as a cause for B, we want to know why. And theories that are able to do this are more acceptable to the scientific community. Plate tectonics, the movement of continents and land masses through subduction and abduction, is now a well-established phenomenon. Lava rises, creates new crust at the edge of a continent, and subduction sucks down land at the other end, and movement occurs. When Alfred Wegener, early in the 20th century, first proposed the movement of plates, nobody took him seriously because nobody could think of a mechanism by which this happened. They all agreed that if you folded South America into Africa, it looked like they had once been together. But in the absence of a mechanism, it was the most wild kind of speculation. Once we had a mechanism and we had other proofs in the form, for example, of similar minerals being located precisely where continents had diverged, this was taken as strong support for the theory. But there's a more fundamental problem with positivism when we come to how it's applied in the sciences. And this has to do with the long-standing goal of trying to create theories that are universal and ultimately that fit in a hierarchy so that not only is everything explained, but all the parts fit together neatly. Increasingly, scientists, beginning with physicists, but spreading to the other scientists, now think this is probably an impossible goal. The best we're going to do, a philosopher of science and physicist Nancy Cartwright argues, is to develop understandings within individual fields of science and at particular levels of analysis. We might be able to explain something at the molecular level, at the level of everyday existence that we observe, and perhaps at the astronomical level. But to think that these explanations would all fit neatly into one package is highly doubtful. So rather than having a hierarchy, she suggests we'll develop something more like a collection of balloons that will be roughly related to one another, but their positions will change over the course of time. And if this is so, then the long-standing project of theories that explain everything is highly questionable. So too is reductionism, which is part and parcel of this approach to both physical and social science. Reductionism, you remember, is the attempt to explain macro-level phenomena at micro-level terms. I used the example in my previous talk of explaining the phase transition from ice to water to gas, which we can do so very neatly if we examine molecules and their energy levels. Now, what's increasingly happened in physics and biology, in other sciences, is more and more interest in bottom-up understandings. And they often take the form of processes. So consider evolution. It's a theory of process. It tells you the kinds of things that bring about change. Genetic drift, evolution, genetic change, and selection through a process of survival of the fittest, so that only the most fit live to the age of reproduction, and progeny over time develop characteristics most consistent with survival, so their structure changes, and this is what we call evolution. This is not really a reductionist theory in any way, nor for that matter are theories that focus on the processes by which interactions at one level of analysis produce something at another. Famous examples of this in social science are Adam Smith, who talked about the invisible hand, which is a process. The baker is motivated by a desire for profit, to look after his family and have better things in life. So he produces bread and sells it, and tries to produce possibly better bread than the bakery down the street for this reason. Over time, with enough people doing this kind of thing, Smith reasoned, we would have economic development. So there would be a system-level result from individual-level behavior. This is a bottom-up explanation that focuses on process. Now, within the physical sciences, there is also quite a different understanding of why we accept something as possibly true. And I've noted that both verification and falsification play a role here. The question is, who decides? And here, Karl Popper, late in his life, came around to the understanding of science as a practice. That what is good science at any given time is what good scientists think it is. And these are people who have been trained in doing their science, in assessing not only their work but others. They've served on committees and boards to give grants, to evaluate work for journals. They've seen and perhaps participated in the development of new ways of evaluating claims. Central to this is the understanding that it's not a static process. It's constantly changing because people challenge the rules that are being used to determine whether something is valid or not. If they make interesting and persuasive challenges, over the course of time, the science changes. So the practice of science is what counts, but it's an evolving practice. And the authoritative spokesmen of it are the top, most respected scientists at any moment. Papa was very clear that this makes science an ethical practice and puts a particular burden on those top scientists who are the gatekeepers in their field. Now, I have been hoping in this talk to also cover the interpretivist understanding of how we make knowledge claims, but I don't have time. So I'm going to end this talk a minute or two early. And in my next talk, we'll look at interpretivism and then compare it with positivism. Thank you.